Actually, can you please repeat actually? Hello? Uh, yeah, Sunday and Tuesday. Yeah, yeah, Tuesday. Uh, I don't know about that session. I don't know about that session actually. I'm not sure about that. So we will start at 3 p.m. We'll just wait for some more minutes, and then we can start. Yeah, Vijay, you want to say something? You can use your mic now. Okay. Okay, okay. No, yeah, I got that. I got that. Which one? Hmm. I think two guys. Actually, on Sundays there are two sessions, and one is on. Sorry, on Sunday there are two sessions, and on Tuesday there is one session, right? And I think there's a scholar from IISc that conducts a session at this time also. I don't know. I don't know his name, but a link will be available in the portal. You can just check once again if you want to join that session or if you want to join this session. Have you joined that session before? That when week 9, 10 last week on Sunday. Okay, then link should work. I think link should work. Try again if you want to. If you want to join that session, no problem. So if you can please mute your mic, I think we can start. It's only already 3:04. So let me just share my screen first. So, good afternoon, everyone. My name is Musab Rafiq. I'm the coach for this course, Digital Circuits, that is taught by Professor Shantanu Chattopadhyay from IIT Kharagpur. I'm a PhD scholar at IIT Kanpur in the Department of Electrical Engineering, and in this session, we are going to discuss problems related to microprocessor 8085. This is our second last session, and next week we'll be having our last live session, that is week 12 live session. That will also be, I think, related to microprocessor 8085. So this was the introduction. In case of any queries or doubts regarding a particular problem, sufficient time will be given after every particular problem is solved. You can type in your doubts. If you have any queries, you can type in your doubts, or you can use the microphone to have your doubts addressed. So without further ado, we can start, and new participants will be only admitted after a particular problem is solved. So before we start with our particular problem, let me just give a brief overview. We'll not discuss in detail, just brief overview, some 2-3 minutes brief overview of architecture of 8085. So this microprocessor 8085, it is a 8-bit general purpose microprocessor. It consists of the following functional units. So it consists of the arithmetic logic units, which is responsible for carrying out all arithmetic operations like addition, subtraction, multiplication, increment, decrement. And this arithmetic logical unit also perform logical operations, the bit shifting operations, and other arithmetic operations. Also, we have this flag register. It is an 8-bit register that stores 0 or 1 depending upon the value in accumulator. So it's an 8-bit register, but only 5 bits are important, and the other 3 bits are don't care conditions. Also, we have this accumulator, which is a 8-bit register. It is used to perform input-output arithmetic and logical operations. It is connected to arithmetic logic unit and the internet data bus. Arithmetic logic unit and internet data bus. It is the heart of microprocessor because for all arithmetic operations, ALU is connected with the 8-bit pin to ALU. And also we have the general purpose register. There are 6 general purpose register. These registers hold 8-bit values. These 8-bit registers are B, C, D, H, and L. Also, we have 2 temporary registers, W and Z. These are reserved registers. Also, we have this program counter, which holds the address value of the memory to the next instruction that is to be executed. And we have the timing and control unit. It comes under the CPU section, and it controls the flow of data from the CPU to the other device. And we have this interrupt control. Interrupt control is basically when our main program is executed and we request some other program to be executed, the main program gets stopped and the requested program is executed, and after the requested program is executed, the main program is again executed. So there are 5 interrupt signals. These are trap, reset 7.5, reset 6.5, reset 5.5, and enter. The priority order is trap is greater than reset 7.5, reset 6.5, reset 5.5, and then finally interrupt. And then we have this data bus and address bus. Data bus is bidirectional and it carries the data which is to be stored. And we have the address bus which is unidirectional and it carries a location where data is to be stored. This was just a brief overview. I think you guys will have gone through these things in the week tutorials. This was just to give the brief overview, not in detail. So you know that if you want to go in details of the microprocessor 8085, you can refer to this very good book by Gonkar, Microprocessor Architecture, Programming and Application with 8085. A really nice book. You can just refer that. So some people have joined in. Let me just admit them. Then we can start with our first question. So let me just start with the first question of today's live session. So, as we discussed before, so let me just start with the first question. And the first question asks us, how many flags are there in 8085 microprocessor? You saw that just now I discussed that flag is an 8-bit register, but only 5 bits are of importance and 3 bits are don't care. So 8 and 5 are important and 3 are don't care. So these 5 are the number of flags there are in microprocessor. So what are these? These are number 1 is sign. So the values of these 5 bits are depending upon the value stored in the accumulator. Sign. Then we have parity. We have carry. We have auxiliary carry or carry auxiliary. I'm not sure about the name exactly. I think, let me just check. Auxiliary carry. And then we have sign, parity, carry, auxiliary, and then we have 0. So this is 1 whenever the value stored in the accumulator is negative, and this is 0 when the value stored in the accumulator is positive. This is 1 when the value stored in the accumulator contains even number of ones, and 0 when the number of ones are not even. This is carry when after a particular operation a carry has been generated. So this flag gets set to 1 for a carry and 0 for not carry. Auxiliary carry is for in a BCD calculations when there is a carry from D3 bit, that is 4th bit, to D4th bit, that is 5th bit. So this gets 1. Otherwise, if this thing doesn't happen, a pass of 1 doesn't happen from D3 to D4, this thing remains as 0. And we have 0 carry this flag whenever the we have after operation the contents of the accumulator are 0. So this is 1, otherwise it's 0. So these are the 5 flags that are there in microprocessor 8085. So let me just check if someone has joined in or not, and then we can proceed to question number 2. So no one has joined in. I think we can proceed to question number 2 if that's fine with all. Also, let me just draw this one here. This is like this, 8 bits, 1 2 3 4 5 6. This is D0. This is your sign, this is your 0, this is your auxiliary carry, this is your parity, and this is your carry. Just now we can move forward to the next question. This question states that the program counter stores a address of the current instruction executed by the processor, b address of the previous instruction executed by the processor, c address of the next instruction to be fetched from the memory, D none of the above. So as already discussed, I discussed briefly in the intro section, the program counter stores the address of the next instruction to be fetched from the memory. Just a moment. So the question asks us, which of the following is not a valid 8085 instruction? Can't find my cursor. So it states that which of the following is not a valid 8085 instruction? A LDX, B LDXH, C LDXD, and then INR M. So for a LDAX, the syntax is LDAX followed by RP, which RP signifies the register pair, and this register pair can only be BC and DE. So as per the given question and in the given options, this thing doesn't satisfy the syntax. So option B is our correct answer. This is not a valid 8085 instruction. The correct syntax has to be LDX register pair, where BC and DE are the only register pair that can be used in this instruction LDX. Moving forward to the next question, we have this thing, which of the following flag. So we discussed it like this. We are just 5 flag signals in a flag register. So this question asks, which of the following flag is not infected by CMP and CPI instruction? So what is the CMP? CMP is a 8-bit instruction, which means compare, and CPI is also a instruction, but it's a 16-bit instruction where the next 8-bit after the first 8-bit, the next 8-bit specifies the data. So the carry the flag that is not affected by the CMP and CMPI instruction is this parity flag. So what basically happens in this CMP and CMPI instruction? So we have this accumulator A, and we have this another value that is stored at some register or memory. So if a is less than that value in the register, then carry flag is set to carry flag is set and zero flag is reset. If a is equal to that value in register and memory, the zero flag is set and carry flag is reset. And if a is greater than register and memory, the carry and zero flag are reset. So as you can see with this instruction, these three are affected, but this thing, this flag, parity flag, is not affected. So we can say that the following flag is not affected by this compare and CPI uh, instruction. So our answer is parity flag is not affected. So option D is our correct answer. Let me just check if someone is been in the meeting or not. Yeah, I'll just repeat the operation once again. So if value in the register was less than that in the register memory, the carry flag is set and the zero flag is reset. And if a is equal to the value in the register memory, the zero flag is set and the carry flag is reset. And if a is greater than the register memory, the carry and zero flag are reset. So moving to the next question. The next question is find the total delay. So next question is find the total delay produced by the following program. Assume that 8085 microprocessor. So you know this symbol. This is basically this signifies micro. I think you guys must be knowing that, but still micro, and P is short for here processor. So keep this thing in mind. Maybe in future you might have this thing. So the question asks us find the total delay produced by the program. Assume 8085 microprocessor is running at 2 MHz clock. So we have this move immediate C0EH, then we have decrement C and jump to non-zero loop. So my program is MVI C0EH. So this takes us how much t states? So let me just check. This takes up 7 t states. You guys must be knowing about these things. If not, you can refer to your notes and or book to get familiar with this. So it takes up 7 t states. Then we have this loop. So in C, the value is C consists of 0, 0, 0, 0, then 1, 1, 1, 0. Basically 14, you can say. And then we have loop. So decrement the value of C. So value of C gets decrement by 1 after every iteration. So this thing takes up 4 t states. And then we have jump to non-zero loop. So if it's a non-zero, it will go back to this again. So one thing here should be noted that for a successful loop means if this condition is satisfied, it will take up 10 t states. Otherwise, if the condition is not met, if this is a fail, then it will take only 7 t states. But let's just consider if it's met, it takes up 10 t states. So this loop thing takes up together 14 t states, right? 10 plus 4. So loop takes up 14 and this loop will be executed 14 times because the value of in this C is 14 and we are decreasing it by one value. So number of t states for a loop in total will be 14 multiplied by 14. But as I told you, the last iteration this thing will not be met. So only at that time only 7 t states will be taken. So we have to minus that 3 extra 3 that we considered here. So it will be minus 3. So 14 square will be, let me just compute the 14 square. 14 square will be 14 multiplied by 196 minus 3. So this thing will be equal to 193. So total t states will be equal to, let me just write it here. Total t states will be equal to 193 plus 7 from this, so it will be 200. So my total delay will be 200 t states. So we have this. Let me just use the next blank slide for rest of the computations. So we have 200 t states, and my clock is given as 2 megahertz. So 2 megahertz will correspond to clock of period 1 by 2 megahertz. So this will be 1 by 2 into 10 to the power 6, and my total delay would be then my delay period of one cycle multiplied by the number of cycles, that are 200. So this is 200 by 2 is 100 divided by 10 to the power 6. So this is 100. This is equal to 100 into 10 to the power minus 6, and this 100 into 10 to the power minus 6 is simply 100 microseconds. So if we just check if is there any option in 100 microseconds? Yeah. So the correct answer to this question is option A, 100 microsecond. So if there are any doubts regarding with question number 5, you can just ask them. I think there are no doubts. We can proceed to question number 6. Question number 6. Let me just go to question number 6. So question number 6 is a theoretical question. It states that how many t-states are required to execute the following instruction. So it is LXID 2589H. So you must be knowing that this instruction, you can just refer to your notes and lecture slides, that this instruction takes up 10 t-states. So this was a pretty much theoretical question. Simple straightforward answer. So this thing takes up 10 t-states. So now we can move forward to this question number 7. So question number 7 states that, excuse me. So question number 7 states that in the following 8085 assembly language program, assume that the carry flag is initially reset. What is the content of accumulator after the execution of the program? So we are given this program. So we have been asked that after the execution of this program, what will be the contents of accumulator. So we have to find out the contents of accumulator. So how will we do it? We have this thing first, MVI A, that is move immediate A 04H. So what this thing essentially does, our accumulator gets loaded up by the data 4 0 0 0 0 1 0 0. This is my contents of accumulator of the first instruction. Then we have rotate accumulator right, represented by written by this instruction RRC. So what this RRC basically does, it divides the contents of accumulator by 2. Basically, when you shift this any binary number by shifted by one digit towards the right, my value of this gets divided by 2. So it goes to rotate through accumulator to right, and the value will be, so my value in the accumulator after this operation will be, if I shift it to the right, it will be 0 0 0 0. Then this one will go here 0 0 1 0. So it was 0 4 here, it will be 0 2 here. This is hex. Then we have, so then what we are doing, we are putting this value of accumulator in register B. So my B will be now 2. So it will be 0 0 0 0 0 0 1 0, and my A is already 2 here. Now we are moving the accumulator contents to left RLC by using the condition RLC. So it was 2, sorry, now it will be 4. So we are shifting it by one bit towards the left. So it will be 0 0 0 0, then it will be 0 1 0 0, and then we are doing it again, RLC, so it's twice, don't get confused. So we are again shifting it by one bit, so it will be, my A will be equal to 0 0 0 0, then 1 0 0 0. So my content of the accumulator is 08 as of now. So then what are we doing? We are adding B to A by using this condition, add B. So this A will get added to this B. So let me just do it on the next page, or we can simply do it here. So what is happening? We are having this 8 and we are adding it to 2, right? So 8 plus 2 is simply 10. When you add 8 with 2, it's 10. So we are having this 10, so my contents of A will be now 10. So 0 0 0 0, then I have this 1 0 1 0, so this is 10, and I'm rotating by right, that RRC, rotating accumulator by right, so I'm just shifting one bit towards the right, that is a divide by 2 operation. It will be simply 5, but let's just shift it by one bit, so it will be 0 0 0 0 1 0 1. So this thing is now 0 5, 4 plus 1 is 5, 0 5 H. So my contents of the accumulator after the execution of this bit of program is 0 5 H. How much is it? 0 5 H. So if I just check it, if there is any option, yeah, option A is my correct option. I can see there are no doubts. I think we can proceed to question number 8. So the question number 8 asks us, what are the contents of the accumulator after the following program is executed? So we are given this thing, uh, this bit of program, and we are asked to find the contents of accumulator after this program is executed. So we have a loop thing here, so we'll just divide our in iteration kind of thing. So what this thing does, this LXI it loads the BC register here. So we have this LXI RP. So here RP is B and C. So B gets loaded by 04 and C gets loaded by 00. So we have this thing as iteration 1, this thing as iteration 2, and so on, depending upon when the program will be executed. So here we have the instructions LXI BC. So what will it do here? This is iteration number 1. So B will be, as per question, B will be 4 and C will be 00. So then I am going into loop. So my this instruction decrement B, so I'll just write this decrement B will take place. So my value of B was 04, so after decrement B, that is value of B gets decreased by 1, so it will be 03, and my A will be that is the contents of C will be moved to A. So my A will be, so this is move A comma C, contents of A will be that of C, so this will be 0 0, and then the OR A B, that will be OR operation between this B and the contents in the accumulator, that will be the number itself. So that will be OR operation. You know that OR operation happens when I'm having this OR operation here. So the OR operation occurs between this register B and the contents of accumulator, and the result gets stored in the accumulator itself. So this thing is OR A B. So OR of 03 with 00 is simply 03. So my A will be now 03, because you must be knowing from your basic knowledge of this, what is this called, binary operations, A or 0 is always equal to sorry, A or 0, not or A or 0. So this will be 03. So this loop is successful, it will go back to this value here. Now my B is 03 and my C is 00. Now I'm in the loop, so my value B gets decreased by 1, so my B will be now 02, and contents of C will be moved to A. C is 00 only, so A will be 00, A will be 00. Now OR operation of B occurs with A. B is 02 and A is 00, so it will be B only, so A will be 02. And so this loop is successful. Then as I go back here again, now my B is 02, decrement by 1 will happen, so it will be 01. The contents of C will be going to A accumulator. C is 00 only, so it will be 00. Now OR operation will happen between them, and A will be 01. It's a non-zero value. It will again go back to this loop thing. My B was 01, now it will get decreased by 1, so it will be 00. A will be 00, and the OR operation of A with B, 00 OR with 00 OR with 00 is 00. Now this loop will be terminated and program is executed. So the program will be executed when A will go to 00. So my value of the accumulator is simply 00 after the end of program. So I think this portion was clear. This was question number 8. Yeah, this was question number 8. Now I think we can move towards question number 9 of today's live session. So the question number 9 is again we have to find out the contents of accumulator. Just a moment. So we have to find the contents of accumulator after the execution of the following program. The program is first we have to there is a value of A is given this 4e, then B, then this AND operation, then XOR operation. So let me just start. So what we are doing here, so we are putting the value of A equal to, using this instruction we are having hash 4e(x). So the value of accumulator gets updated by this value 0 0 0 1 0 0 4e. E is 14, so 8 plus 4 is 12, 12 plus 2 is 14, so this is 4e, right? This is 4e, and in register B I am just putting 10x 10x, so this is 0 0 0 1, and this is only 0 0 0 0. So now what I am doing, I am having this thing. This is, let me just write it first here. This is the AND operation. What it does is, this is a mnemonic. AND is a mnemonic for AND operation. What it does is essentially it does the AND operation between the value stored at this register B with the value at accumulator. So we have this A and A of register B. So this thing will be ANDed. So after AND, the contents of AND one thing, after this thing, the contents of register accumulator will be updated by the answer of this AND operation. So let me just do the AND operation of this thing. This will be 0 and 0 is 0, 0 and 1 is 1, sorry 0, 0 and 1 is 0, 0 and 1 is 0. So I think this will be 0 0 0 and 0. So this is contents of, and this is not there, this is not there, 0 0 hex. Now what we have to do, the next part of the instruction, we have this XRA B. So what is this XRA? This is simply a mnemonic for XOR. So the contents of register B will get XORed with the contents of the accumulator. So XRA B. So this B has contents 1 0. You can see it here. So this thing will be XORed with 1 0. So if you XOR it, it will be 0 0 is 0, 0 0 is 0, 0 0 is 0, and 0 0 is 0. 1 XOR with 1 is 1, then all others are 0 0. So this thing is 0 1 0. So the contents of the accumulator after the execution of the following program is 10x. If there are any doubts, please type in. And if someone has joined in, let me just admit them. I see there are no doubts regarding this question. We can just proceed to question number. Where were we? We were at question number 9. So now we are at question number 10. The accumulator contains 0 of B hex and B register B contains 1 2 hex. What are the contents of A and B after the given given instruction is executed? So the instruction is OR of B. So what will it do? It will be OR with A. This is simply what it will do, and the results will be stored in accumulator. Results, don't get it. This is the results in accumulator. So my A is 0 FB. So this is FB hex. So F is simply 1 1 1 and 1. B is I think 11 8 plus 2 plus 1. Yeah, so it will be 1 0 1 1. 8 plus 2 is 10. Someone has joined me. Let me just admit the person. Let me just read the question number 10 once again. The accumulator contains 0 of B hex and B contains 1 2 hex. What are the contents of A and B after the given execution and instruction is executed? This is ORAB, so this is simply an OR operation of B with the contents of the accumulator, and the results are stored in the accumulator itself. So A, we have this thing as FB hex, so this is 1 1 1 1 1, and B is 1 0 1 1. So 8 plus 2 is 10, 10 plus 1 is 11. Yes, and then we have B has contents as 1 2 hex, so this is 0 0 0 1, and 2 is simply 2 simply 0 0 1 0. So this was FB hex, this is 1 2 hex. Now the execution instruction that needs to be executed is the OR operation between A and B. So let's just do the OR operation. So it is 1 XOR with, so 1 OR with 0 is 1, 1 OR with 1 is 1, so this is 0 OR with 0 is 0, this is 1 OR with 1 is 1 OR with 0 is 0, sorry, 1 OR with 0 is 1, this is 1, this is 1, this is 1, and this is 1. So this is the result of my operation, and this result will be stored in the accumulator. So my contents of the accumulator will be 1 1 1 1 1, that is F, and 1 0 1 1, so it's 8 plus 2 10, 10 plus 1 11, so this is FB. So my contents of the accumulator after this OR operation instruction is executed, it will be FB hex, and my B will be remain unchanged. It will be simply 1 2 hex. I can't find my pointer. Yeah, 1 2 hex and FB hex. So the option B is correct option. Now moving forward to the next question. This is question number 11 of today's live session. So question number 12 asks us, what are the contents of the accumulator after the following instructions are executed? Is move, so putting this to a 1 2 hex in A, then we have this CPL, so this CPL is simply complement, then we are adding the 1. So what we are doing is we are just putting this A, having this move A, and we are just simply having the contents of accumulator as 1 2, so 0 0 0 1, and 2 will be 0 0 1 0. So this is my 1 2 hex. Then my next instruction is CPLA, so I'm just complementing it. So this will be 0, sorry, this will be all the zeros will be 1 and all ones will be zeros after complement. It will be 1 1 1 0 1 1 0 1. So this will be 8 plus 4 is 12, 12 plus 1 is 13, 13 is I guess D, and this is 8 plus 4 is 12, 12 plus 1 is 8 plus 4 is 12, sorry, this was 8 plus 4 12, this was 14, this was E, and this is This thing is 8 plus 4 is 12, 12 plus 1 is 13. This was D. Yes. Now finally we are just adding 1 to the accumulator. We are adding 1. So we are just adding 1. So what will happen? We are just adding 1 to this. So 1 plus 1 is 0, 1. So 0, 1 will go to carry. So this will be 1. Then all will remain same. 1, 1, 1. So this is 8 plus 4 is 12. 8 plus 4 is 12. 12 plus 1 is 13. So this 8 plus 4 is 12. 12 plus 2 is 14. So this will be E. This is 8 plus 4 12. 12 plus 2 14. And so this is also E. So my contents of accumulator will be A is equal to EE. So my option B is correct answer. So if you just carefully look at this set of instructions, what it essentially does is it's basically 2's complement. These three instructions together does 2's complement. How? So first we are doing 1's complement, and then we are adding 1 to the 1's complement result, so we'll get 2's complement. So this was basically 2's complement. So we are done with this question number 11. Now we are having our question number 12 of today's talk. So question number 12 asks us which of the following instruction is an example of implied addressing mode. We have this CMA, then we have this ORIA, then we have this LDAA, MVIB. So what is this implied addressing mode? It's basically where no operand is specified in the instruction. Data is available in the instruction itself. So like we have this RLC as we saw earlier, RRC, and among the given set of instructions, these are the immediate mode of addressing, and this is the implied mode of addressing, CMA. Now towards the next instruction, next question. What are the contents of register B after the following instructions are executed? So we are given, so what are the contents of register B after the following instructions are executed? So we are given this MVI move immediate B, then move immediate C, then increment XB. We are required to find the contents of register B after the following instructions are executed. So once I do MVI B FF, so my contents of register B will be equal to like this. Then I am doing MVI C FF hex. So my contents of register C will be like this. Then I am doing INXB. So INXB basically has a syntax INX register pair. So when I write INXB, it simplifies INXBC. So this increments the contents of register pair. So here the register pair is BC as one entity. So whatever the contents of the register pair BC was, it will increment them as one entity. And once you increase the contents of this BC by one entity, the contents of the register B will simply be turned to 0000, because simply once you increment this thing like this, if you just put them in one line, these 8 bits and these 8 bits, and then increase it by 1 bit, all of them will be turning to 0000. So it will be like this. So the contents of register B, which is this thing, will be 00 hex. Option B, 00 hex. Now moving towards the last question of today's live session, and this is question number 14. This is just the related to this VHDL code. We have this, consider the following program, VHDL code. What does it represent? We have this process, then we have this begin, then we have this clock is assigned this value 0, and then we have this wait for 20-second thing. Then we have this clock is get assigned value 1, then we have this thing for 12 nanosecond, and then end process. So if you just look at carefully, what it does is, so as the process begins, we have this zero thing for 20 nanoseconds. Then the clock value gets assigned as 1 for 12 nanoseconds, so it will be 32. Then it will be 0 for 20, again 20 seconds, so this will be 62, sorry, 42. Then it will go for 12 nanoseconds up for it will go to 12 nanoseconds, it will go high for 12 nanoseconds. So what it essentially does, it has this a clock with on time of 12 nanoseconds. So one thing interesting to note here is that there is nothing here in this sensitivity list. So this is a never-ending process, so it will produce a clock having on time of 12 nanoseconds. So that was all for today's live session. If you have any queries, you can just type in or use your microphone. And also, this was our second last session, and next week we'll be having the what we call as the last session of the this course, that is week 12. It will also be related to, I think, the microprocessors. So Dr. Bikramendra Das has asked me to repeat the question number 3. So I'll just repeat the question number 3. Let me just check what was question number 3. So this asks us which of the following is not a valid 8085 instruction. So at first the syntax and the given instruction LDAX is not the valid syntax valid instruction, because LDAX is written as like this LDAX register pair, and the only valid register pairs that can be used here for this LDAX are B and C register pairs and D and E register pairs. H and L register pairs are not valid with this instruction. That's why it's not a valid instruction. So question number 1. So question number 1 asks us how many flags are there in 8085 processor. So a flag is a 8-bit register, but only 5 bits are important and 3 are don't cares. So there are 5 flags, basically 5 signals. One is sign, then is parity, then is carry, then is auxiliary carry, and finally we have this zero sign, zero flag. Sorry. Yeah, yeah, it will be uploaded to the book, and the name of the book is Microprocessor Architecture, Programming and Applications with 8085. This thing actually, yeah, lecture, yeah, it will be uploaded in this what do you call it, Swayam portal. It will be here only. And this is a really nice book. So if you want to get acquainted with this 8085, I remember that I referred this book in my BTech days. So although we are not using this 8085 thing right now, but Gonkar, Ramesh Gonkar. I'll just type it. Ramesh Gonkar. I think this is also your prescribed book. Once I referred this course catalog, this was the referred book. This is a standard book for 8085. So Nitesh wants me to repeat question number 12. So let me just check what is question number 12. Is my screen visible or I have stopped sharing it? Okay, so it's a question number 12 asks which of the following is an example of implied addressing mode. It says instruction CMA. Other, because this thing constructs basically this implied addressing mode has no operand specified in the instruction. You can see there is no operand specified in the instruction. Data is available in the instruction itself. For example, we have this RRC instruction. Here, no operand was specified. You know that contents of accumulator were to be shifted by write, and the results were updated in the accumulator itself. Just like that, this CMA instruction is also an implied addressing mode. I just forgot this. What is this CMA instruction exactly? Let me just cross check it with my notes. This CMA instruction. Okay, this is basically complement the accumulator. So what it essentially does, it complements the accumulator. So you see nothing is specified in the operand. So whatever the contents of the accumulator over there, they get complemented by they get complemented, its value gets complemented, and the results get applied in the accumulator itself. That's why it's the example of an implied addressing mode. So if there are no further doubts, we can just end the live session today, this live session right now, and we can meet next week, that is 16th of October, 3 p.m. Thank you guys for joining.